Hi everyone. So today we're going to start talking about electrons, and to do so we're going to first focus on the Bohr model. So the Bohr model, also known as the planetary model, shows that the electrons are in an orbit around the nucleus in its constant circular motion, much like how the planets are revolving around the sun. But this model is actually assuming a few things. Now, the first thing that this model is assuming is that the electrons are only able to occupy certain energy levels. So each ring is at its own unique energy, and that these electrons can only ever occupy a certain one, and they can never really exist in the in-between region. Okay? But it is possible for these electrons to actually jump between energy levels and move between them. When an electron actually does jump from a lower energy to a higher energy, that process is referred to as excitation. Now, when that electron loses energy, it goes back down to what's called the ground state. So the electron is actually able to move between these energy levels or these different rings if it has sufficient energy to do so. But we'll actually talk more about that later time when we discuss light and other processes involving it. So the issues with the Bohr model is that while it predicted information and behavior of the electrons for hydrogen correctly, it was pretty limited to just this element. It couldn't really explain how come only certain energy levels are allowed, and it didn't really do much in terms of explaining how the atoms actually bonded together. So in terms of our understanding of the electron, it was pretty limited by the Bohr model. It wasn't until the French scientist Louis de Broglie did he propose an idea that the electron, which is a particle, might also be able to behave as a wave. So this created this idea called particle-wave duality. Particle-wave duality is this concept that the property of a particle can actually behave like a wave, and a wave might actually be able to behave like a particle. Doing so opened up a brand new way to approach and to view the electron, and it actually started the exploration of what's called quantum mechanics. So instead of treating the electron solely as a particle, they now had this idea that they can take a look at the electron as actually a wave rather than a particle that actually has properties of both. So to understand quantum mechanics is to also understand the difference between classical mechanics. Now, mechanics is all about the behavior and the motion of an object. The reason why we have to specify this is because of the fact that objects have different sizes to them. And if we're going to assume the wave-like properties of particles, well, that can only ever be applied to something that has a very, very small mass. Take, for example, a golf ball and an electron. We know the size of a golf ball. An electron is significantly smaller than a golf ball. If we are to assume that they both behave like waves, well, the wavelength of the golf ball is so small, it's actually negligible, while that of an electron is pretty reasonable to work with. So the fact that the wavelength of the golf ball is really small means that these wave-like properties aren't really all that apparent and can basically be ignored at this point. So we have to distinguish between the two if we're going to talk about their motions. So classical mechanics is how we describe the movement of something large, while quantum mechanics describes the movement of subatomic particles and atoms. Here we can actually treat them as if they were waves. So whenever we talk about quantum mechanics, we're actually going to be talking about the movement of particles and atoms, and we're going to think of them as if they are moving as a wave would. So moving on to quantum mechanics and this new approach of how the electron is going to behave in this manner, it led to the development of what's called the quantum mechanical model. So this was actually devised by Ernst Schrödinger, in which he created a mathematical equation that actually helped to describe the behavior in an electron. So this equation right here, known as Schrödinger's equation, just like Schrödinger's cat, actually helps describe the energy and the position of the electron. So the quantum mechanical model is similar to the Bohr model in that it only allows certain energy values, but unlike the Bohr model, there's no assumption onto the path of the electron, meaning the electrons can be anywhere in this space. It's not going to be going in a circle. It does not make that assumption, unlike the Bohr model does. So, building off of Werner Heisenberg's idea, he elaborated that rather than just trying to find the motion of a particle, okay, it's better to actually look for the probability of it. Where is it more likely to be? And Schrodinger's equation actually helps to find the more probable locations of the electron where it can be. Solving this equation gives you a value for where the electron is most likely to be and at what energy. And this is the basics to quantum mechanics, quantum chemistry, quantum physics. Basically anything quantum revolves around this equation right here when studying the electrons. And in a moment, we're going to go over how to use this equation and how it actually led to help us figure out where the electrons are in an atom.